Welcome to the next module of the class. What we'll be looking at this week are what are called the rules of replacement in natural deduction. In total, there'll be 10 such rules, and in this video, we're going to be looking at the first 5. Now, the various valid argument forms we've seen so far, what we're calling the rules of implication, are powerful tools of inference and will take you far in terms of dealing with arguments and constructing proofs. But unfortunately, they are not enough to do the job alone. There are very many valid truth functional arguments whose validity cannot be proved using only the 8 rules that we've discussed so far. And so what we need to do is expand these set of rules and to increase basically the tools that we have at our disposal to deal with these kind of complex arguments. To offer an illustration of the problem, consider the following argument, an argument which is valid. If you travel directly from Chicago to Los Angeles, you must cross the Mississippi River. If you travel only along the Atlantic seaboard, you will not cross the Mississippi River. And therefore, if you travel directly from Chicago to Los Angeles, you will not travel only along the Atlantic seaboard. Now, the first thing to note is that is very clearly a valid argument. And translated into symbolic notation, this argument appears along these lines. Premise 1 says, if D, then C. Premise 2 says, if A, then not C. And the conclusion drawn is, if D, then not A. And it's clear that this conclusion does follow from the given premises. But try as we might, there is really no way to prove that this is a valid argument using only the rules of implication that we've seen. And so the question here is, if the rules we've seen so far are inadequate for this task, what is missing? Or what do we need to do or add to this to allow us to solve for arguments like this? What is missing here is essentially the ability to replace one statement by another that is logically equivalent to it. We need to be able to put in place of any given statement any other statement whose meaning is exactly the same as that statement that is being replaced. And so we'll need rules that identify legitimate replacements precisely and clearly so that we can do this. And this is what we're going to be studying in this module. We can define a rule of replacement as such. A rule of replacement is a rule that permits us to infer from any statement the result of replacing any component of that statement by any other statement that is logically equivalent to the component replaced. So let us now examine the first 5 of our logical equivalencies. We will use these rules of replacement frequently and will often rely on them in constructing formal proofs of validity, so they're very important, and we will need to understand their use as clearly as we do the various rules of implication. Now, the first thing to note here is that when we express the rules themselves, the rules of replacement are stated in the form of logical equivalencies. And so we'll have to introduce a new symbol to show this. The symbol is the double colon. And when we see this, what we are designating by way of this particular symbol is the idea of a logical equivalency. In this particular case that we see here, we are saying that P, whatever P stands for, is logically equivalent to Q, whatever Q stands for. Now what this means and what the symbol tells us is that the expressions that sit on either side of the double colon have the exact same truth value, regardless of the truth values of their individual components. And what this means in the context of a proof is that these propositions can simply replace one another. We can swap them out willy-nilly whenever we feel like it without changing the truth value of the actual argument. So let's take a look at the first 5 rules here. Now the first rule is one we've seen before and that was very briefly discussed at the beginning of propositional logic. This is De Morgan's law, or as it's also called, De Morgan's rule. And let me just repeat what was said about it then. De Morgan's law is one of a number of important substitution rules, which explains a rule of inference that permits the valid mutual replacement of a negation of an entire disjunction by the conjunction of the negation of both disjuncts, and that permits the valid mutual replacement of a negation of an entire conjunction by the disjunction of the negation of both conjuncts. Now that's a mouthful, but it's a pretty easy rule once you understand it. So let's take a look at an example. It's the same example we used before. It is not the case that Bob will fail the class and that Sue will pass. Of course, it's going to translate into tilde and then in parentheses b dot s. Now it's very, very tempting to look at this and imagine that we could simply distribute the tilde to both terms and keep the and, that these two things are allegedly saying the same thing. But De Morgan's law shows us that this is not the case, and we could actually show this using truth tables. So our original statement, tilde b dot s, cannot be translated into tilde b and tilde s without destroying the truth value of the statement. What De Morgan's law tells us is that we can take this original statement and then we can distribute the tilde to both the b term and the s term only if we convert the and to an or statement. So when I say it is not the case that b and s are true, what I'm saying, if I want to convert it into a logical equivalency, is it is not b or it is not s. And De Morgan's law works the other way around too. If I have an example that says it is not the case that Bob will fail the class or that Sue will pass, again, we could translate this into tilde or not b or s. And once again, it's very tempting to imagine that what we could do is simply distribute this tilde to both terms so that we end up with not b or not s. But like before, this doesn't work. This is not a logical equivalence to the original statement. So we can't simply distribute the tilde without taking care of that operator. What De Morgan's law tells us is that if I want to distribute this tilde to the simpler terms, in this case b and s, it's not enough that I simply do so. What I have to do is swap the or, the disjunction, to a conjunction, an and claim. So if we look at the assertion, it is not the case that b or s is true. This is the logical equivalent of saying it is not b and it is not s. These two are identical statements and they can translate back and forth one to the other. Now, if we want to state this formally, it's going to look like this. If I have the statement, it is not the case that P and Q are true, this is logically the equivalent of it is not P or it is not Q, and vice versa. So if I have the statement, it is not P or it is not Q, this is the same thing as saying it is not the case that it is P and Q. And of course, if we look at the second option there on the bottom, what we see is when I have the claim not P or Q, this is logically the same as saying it is not P and it is not Q, and again, vice versa. If I say not P and not Q, this is a logical equivalent of saying it is not the case that it is P or Q. These are substitution instances for each other. If I see one, I can simply swap out the other without changing anything in terms of the truth values of the particular claims or in the proof. The next rule of replacement we're going to look at is called commutativity, and this is abbreviated with just COM. Commutativity tells us that the order of statements of the elements of a conjunction or a disjunction simply don't matter. We're always permitted to simply swap the terms around, or what we call to commute them, because whichever order happens to appear, their truth values and thus their meanings will remain exactly the same. Now, to show you what this looks like, let's take a very simple example. The statement either Bob went to the grocery store or he went to the park is going to translate into G or P. But if I simply flip my two disjuncts around so that I have the statement either Bob went to the park or he went to the grocery store, these are logically identical to one another in terms of their truth values, and so we can simply swap these one for another whenever we feel like it. And the same fundamental point that we just saw with a disjunction applies to a conjunction. So if I have the statement, Bob went to the grocery store and he walked to the park, notice what we get is G dot P. And if we simply swap the order of our two conjuncts, we get the exact same statement in terms of its truth value. To say Bob went to the grocery store and he walked to the park is logically identical to saying Bob walked to the park and he went to the grocery store. So once again, what we find with a conjunction, just like with the disjunction, we can swap the order of the terms without affecting the truth value of the statement. This is called commutativity. And formally stated, the rule would look something like this. If I have P or Q, this is logically identical to Q or P, and I can swap those things whenever I feel like it. And the same thing is true with conjunction. If I have P and Q, this is logically identical to saying Q and P. So what order we get with these terms is not particularly important in terms of the truth value. And this basic rule tells us that we can swap them around at need whenever it is useful. The third rule of replacement is called associativity, and we will abbreviate this with assoc, A-S-S-O-C. Now, associativity tells us that the truth value of a conjunctive or disjunctive statement is unaffected by the placement of parentheses when the same operator is used all the way through the particular statement. This rule really, whether we're looking at conjunctions or disjunctions, does no more than allow us to group statements differently when the same operator, that is a conjunction or a disjunction, is being used all the way through the statement. Notice what we're talking about here is a disjunction with multiple terms, more than just two. If I say something like either the car is red, the car is black, or the car is white, I have three different disjuncts in this statement. And one way I could simply write this out is to have R or, and then in parentheses, B or W. But frankly, as long as it is a disjunctive statement all the way through, it doesn't really matter where I put the parentheses. So if I want to stick the parentheses by putting R and B together instead of B and W, that is perfectly fine. It is logically equivalent, and so I can swap around the parentheses like this all I want. But it's very important that the operator stays the same all the way through. If it's a disjunctive statement, it has to be a disjunction all the way through the statement for me to move these parentheses around. And the same basic point will be true with a conjunction when I'm using a conjunction operator all the way through the statement. If I have the statement, the car is rather old, off black, and quite reliable, I could plausibly translate this into O dot and then in parentheses B dot R. But once again, where I exactly put the parentheses in such a statement is pretty much irrelevant. If I want to group O and B together instead of B and R, that is perfectly fine as long as all the way through the statement I'm just looking at conjunctions. If I'm mixing and matching things, then I can't simply move around my parentheses. But if it's all conjunctions or all disjunctions, I can move these parentheses around without affecting the truth value of the statement. So the basic rule of associativity is stated formally like this. Notice in the first line I have P or, and then in parentheses Q or R. This is logically identical to saying in parentheses P or Q or R. And the same thing will be true with conjunctions. If I have P and in parentheses Q and R, I can simply move the parentheses so that I get the exact same logical statement by saying in parentheses P and Q and R. These are simply swappable. I can move them around as much as I want. And again, notice in both cases where the disjunctions or the conjunctions are used all the way through the statement that I'm basically dealing with. The fourth rule is called distribution, and we abbreviate this with simply DIST or DIST. So distribution, as we'll see, will have two variants, one that puts together and one that takes apart, basically. The first asserts that the conjunction of one statement with the disjunction of two other statements is logically equivalent to a disjunction whose first disjunct is a conjunction of the first statement with the second, and whose second disjunct is a conjunction of the first statement with the third. Now, once again, that's a mouthful of a rule, but it's fairly simple to understand once we break it down and look at it in terms of examples. The second variant is also rather unwieldy to simply read, but once again, when we look at it in examples, it will be easier to understand. This variant says that the disjunction of one statement with the conjunction of two others is logically equivalent to the conjunction of the disjunction of the first and the second, and the disjunction of the first and the third. The rule is so named distribution because it distributes the first element of the three exhibiting its logical connections with each of the other two statements separately. So let's look at an example. Notice in this case what we have is not just conjunctions or disjunctions all the way through, but I'm mixing and matching, and there are certain rules I can apply when I have this sort of situation. Notice we're talking about necessarily only disjunctions and conjunctions. This is the time when you can distribute. In other cases, it's not going to be so. So notice what we get with the distribution. If I have the claim, Bob went to the grocery store and either bought bread or bought milk, I would translate this into simply G and then in parentheses B or M. Now what distribution basically tells me is that I can take the G and part of this and then distribute it to each of the terms in the disjunction and break them apart, put them back together with the disjunction. So instead of Bob went to the grocery store and either bought bread or milk, I'm going to say either Bob went to the grocery store and bought bread, or he went to the grocery store and bought milk. And so what I do is simply distribute the G and part of this to each of these two terms, B and M, and then I put them together into a disjunctive statement. The second variant basically just swaps the place of my operators, the or and the and claim. In this case, notice we have either Bob went to the grocery store or he walked to the park and sailed a kite. If we wanted to translate this, we get either G or P and K together. And what the rule of distribution allows me to do is take the G or and simply distribute it to the different terms, putting it together with an and. So instead of saying either Bob went to the grocery store or he walked to the park and sailed the kite, I can say either Bob went to the grocery store or went to the park, and Bob went to the grocery store or sailed a kite. And notice the distribution rule allows me to just take the G plus the operator or and put it together with the two terms that are connected by an and into their own individual statements or disjunctive statements. And it's very important to recognize that while I can take the first statement there, G or P and K, and then convert it into the second, I can also take when I find the second and convert it into the first. I can, in other words, undistribute the G and rip it apart from the two terms. So the rule of distribution stated formally with our double colons telling us that these are logical equivalencies would look something like this. In the first line, what I get, notice, is P and Q or R. And what I can do is simply distribute it out so that I get P and Q or P and R. And notice if I have P and Q or P and R, I can also go back the other way and basically say this is the same thing as P and Q or R. And notice then in the second line, we get the same thing, just with the operators swapped around. If the original statement is P or Q and R, this is logically identical to saying P or Q and P or R, and of course the other way around as well. Now the final rule for this video at least is called a double negation, which we abbreviate with just the letters DN, and this is an incredibly obvious and fairly intuitive rule of replacement that we're going to use. This rule simply asserts that any statement is logically equivalent to the negation of that statement, so that pairs of tildes immediately adjacent to one another may simply be deleted or introduced without affecting the truth table of the statement at all. So notice if I have the proposition Bob went to the grocery store, this would translate into a simple letter G. And what the double negation tells us is that this is logically identical to simply it is not G. In other words, it is not the case that Bob did not go to the grocery store is a way of simply saying Bob went to the grocery store. So these are simply logically identical. And if you ever find yourself with two tildes stacked, you can simply erase those and you have the affirmative of the term. And vice versa. If I have simply a proposition like G, I can simply stick two tildes in front of it and I have exactly the same thing using the rule of double negation. So the rule of double negation is very simple and again I think very intuitive. If we want to state it formally using our double colons, we find that P is logically identical to not P, and not P is logically identical to simply the affirmation of P. So if we want a list of our new rules, the rules of replacement that we've seen so far, the first 5, we get De Morgan's law, commutativity, associativity, distribution, and double negation. And I promise you these will be used over and over again. They're very important rules. Notice that these all basically deal with disjunctions and conjunctions in some way or another, except the last one, which simply deals with negations. So let's walk through a few examples of logical proofs that we can do using these new rules. So we'll start number 1 here. Premise 1 of this argument says, if not P, then Q or R. The second premise says not Q and not R, and then the conclusion drawn is simply P. So to set this up properly, we want to start numbering the lines in order 1 and 2, since we only have 2 premises, and then we want to place the conclusion off to the right, separated by a slash. Now, rather clearly, premise 2 here is setting itself up quite readily to be converted using De Morgan's law. If I have the statement not Q and not R, we know, using De Morgan's law, that this has an obvious logical equivalency. And of course, what De Morgan's law tells us is that number 2 here, not Q and not R, is logically equivalent to saying it is not the case that Q or R is true. And then notice what we want to do is simply say, based on number 2, we can use De Morgan's law to establish this proposition as true, and we'll give this number 3. Now notice what we get here, using lines 1 and 3, and then following the rules of a modus tollens. Rather clearly what we find is we can draw the conclusion that it is not the case that not P is true. And of course, notice what happens is in the first line, we have simply a conditional statement, which amounts to if P then Q kind of thing, where the consequent is the entire proposition Q or R. And of course, 3 is denying this. And if you pay close attention to what's sitting in front of you, notice that what we have as a consequent is the entire statement Q and R. And then, of course, line 3 over there takes that and denies it. And this allows us to deny the antecedent on the other side. And of course, if the antecedent is not P, then to deny this, what we would have to say is, it is not the case that not P is true. And that's exactly what line 4 now tells us, following the rules of modus tollens. Now, of course, the conclusion we are aiming at is simply the claim that P is true. And what we have in number 4 is, it is not the case that not P is true. And following the rule of double negation, we can get to our final goal. Because what double negation tells us is if I ever have 2 tildes stacked like this, this is logically identical to simply erasing them. Not P is the same thing as just saying P, and P is just the same thing as saying not P. And so based simply on the rule of double negation, using line 4, we can now get our conclusion, which is just P. And what we've done then is using 2 new rules plus modus tollens, shown that this is a nice valid argument. So let's take a look at a second example, and in this case, one that's a bit more complex. So premise 1 of this argument says it is either P or it is Q, or it is R. And premise 2 says if it is either P or it is R, then it is not S. Premise 3 says not Q, and then our conclusion says it is not the case that it is Q or it is S. So to set this up into a proof, what we want to do is simply number our various premises, in this case 1 through 3, and then take our conclusion, set it off to the side on the right with our last premise separated by a slash. So the first step here really is about dealing with the second premise, where we have P and R together as a disjunction. And so what I really have to try to do at some point is to get P and R put together. And we have P and R in number 1, but they're separated from each other. So technically, the first step is to simply swap the place of Q and P using the rule of commutativity. So instead of P or Q, I can swap that portion of it to Q or P. And then I have Q or P or R. Now remember that the rule of associativity tells me that where my parentheses go in a disjunctive statement with multiple terms really doesn't matter. So I can take number 4, which is Q or P or R, and I can simply move things around so that I get it is either Q or it is P or R. And notice what this allows me to do. If I take 5 as a disjunctive statement where one disjunct is the term P or R and the other disjunct is simply Q, number 3 tells me Q is not the case, so I can simply, using the rules of a disjunctive syllogism, eliminate Q in order to draw the conclusion that P or R must be the case. Notice then in line 2, we have a conditional statement where the antecedent is P or R. And of course, if you take that line and you add 6 now, which is saying P or R, which is affirming that, that means I can affirm the consequent, which is not S. And so using the rules of modus ponens, I can now draw as line 7 the conclusion that S must be true. And so we're getting closer and closer to our conclusion, which is saying it is not the case that it is Q or S. And at this point, we have the statement not Q and not S. And we can get that by simply taking line 7 and line 3 and putting them together using the rule of conjunction. If I have two separate propositions, I can always stick them together into an AND claim without changing the truth value there. And so the final step here is to take that and to convert it into ultimately our conclusion. Notice the claim not Q and not S lends itself rather readily to manipulation by De Morgan's law. So what we find here is that that type of a statement, not Q and not S, can be converted by simply following the rule of De Morgan's law, which means I can distribute out the tilde and then put together Q and S by way of an OR. So notice finally we get exactly our conclusion using De Morgan's law from line 8. We get it is not the case that it is Q or S. And of course, what we've done then is shown that this is a valid argument. And we've done so by way of a bunch of different rules, both from the earlier module and then this one as well. So the last step in this is to walk through some new strategies that we can add to the long list that we've already developed in the last module using the rules of implication. So we can basically now articulate a number of strategies with these 5 rules of replacement. Now the first one, we'll call it strategy 10. That is just continuing the list that we've been working with from before. Strategy 10 tells us a conjunction can be used to set up De Morgan's law. So if you think about it, if I have a claim like this, where I have two premises, one is not P and the other is not Q, and the conclusion I'm aiming at, it is not the case that it is P or Q, I can of course put P and Q together using the rule of conjunction. And then in this case, what I want to do is simply use De Morgan's law to draw the final conclusion, which is it is not the case that it is P or Q. And so using conjunction, I'm able to set myself up into a position where I can now deal with this. And of course, it can be more complex and messy than this. Notice if the premises I have to work with is P, and then the second one is not Q, and then the conclusion I'm aiming at is it's not the case that it is not P or Q, we're doing pretty much the same thing with just an additional step. First of all, notice I can take number 1 and using the rule of double negation, say that P is now not P, and those are logically identical to one another. And then I can take number 3 and 2 and put them together so that I now have the claim it is not P and it is not Q. And then using De Morgan's law from this, we can actually just distribute out that tilde to say it is not the case that it is not P or Q, which is exactly what our conclusion was aiming at. Strategy 11 tells us that a constructive dilemma can also be used to help us set up De Morgan's rule. So if we have an argument like this, where I have in the original premise, it is if P is true, then not Q, and if R is true, then not S, and then the second premise says P or R, rather clearly we can draw the conclusion from this using a constructive dilemma that it is not Q or it is not S. And from that, we very easily get De Morgan's law converting itself into our conclusion, which is it is not the case that Q or S, by simply distributing out the tilde and then changing our operator from an OR to an AND. Strategy 11 says that we can use addition to help set up De Morgan's rule as well. Notice how this works. If I simply have the claim not P, and my goal is to show that it is not the case that it is P and Q, well, I can get there by simply adding. So in this case, remember addition, if I have a disjunctive statement, I can literally stick anything in as a second disjunct and it will still be a true statement, because disjunction is only false if both sides are false, and we've already assumed that not P is correct. So if I take not P, I can stick anything I want, and in this case it'll be not Q on the other side. And from there I can use De Morgan's law to simply draw the conclusion I'm aiming at. Strategy 13 tells us that distribution can be used in two ways to set up a disjunctive syllogism. So notice if I have this particular argument where I have P or Q and P or S, notice that P repeats itself in both of these disjunctive statements, and it's being put together by way of an and that suggests that I can use distribution to pull out P and then put Q and S together in a different way. Now the second premise says not P, and the conclusion is Q and S. So by rule of distribution, I can tug out the P term that is the disjunct in both of these disjunctive statements, P or Q and P or S, and then I can simply put it P or and then put Q and S together with an and. This is how I distribute. So I'm basically distributing out the P from what was distributed in the original statement 1. And then, of course, using number 2 and 3, I now have a disjunctive syllogism that allows me to basically say, since it's not P, it must be Q or S, and that, of course, was the conclusion I'm aiming at. We can also go the other way around. Notice in the first example what we had were two disjunctive statements, and we pulled out a term to put them together with an and. In this case, we have P and Q or R, and the rule of distribution will allow me to put P together with Q and R together with P into different disjunctive statements. So by the rule of distribution, instead of P and Q or R, I can now say P and Q or P and R. And then, of course, using this line 3 and the second premise, which is it is not the case that it's P and Q, I can, using the rule of a disjunctive syllogism, eliminate the entire first disjunct of line 3 in order to affirm whatever's left over, which is the claim P and R, and that, of course, is the conclusion I'm aiming at. Strategy 14 also deals with distribution, and it suggests that distribution can be used in two ways to set up a simplification. So notice if I have this statement, P and Q or P and S, and I'm trying to draw the conclusion that P is true, this is actually fairly simple. What I can do is simply distribute out P by itself and then put together Q and S by the rule or by way of a disjunctive statement. So instead of P and Q or P and S, I get P and Q or S. And from here, using the rule of simplification, I can just drop the entire disjunction in the second premise, because if P is true in the context of P and Q and S, it's true all by itself as well. And so I can get to the conclusion Q now by just tossing out Q or S, but I couldn't really get there until I basically took out P from the relationship it had to Q and S. And we can also go the other way around to notice if I have P or Q and S, and the conclusion I want to draw is P or Q. I can start by distributing P to both of those terms and connecting them with an and. So instead of P or Q and S, I get P or Q and P or S. And now you can see pretty clearly how I'm going to get to the conclusion. The conclusion is trying to say it is P or Q, and if 2 is true, P or Q and P or S, given that it's an and, both sides have to be true for it to be true, and so I can just toss out the second conjunction, P or S, and then I can just draw the conclusion P or Q. Now the last strategy is a very important one. This strategy, strategy 15, it's worth reading this carefully in the book. He'll explain it by way of an example and walk through it very carefully. This says, if the inspection of your premises does not reveal how the conclusion should be derived, then consider using the rules of replacement to sort of deconstruct the conclusion. So if you have some really wildly complicated conclusion, start tearing it apart using the rules of replacement in order to see if you can find a place to begin. Now notice, if we go all the way back to strategy 1, Rule 15 or strategy 15 is really referring you back to this in a certain sense, because a beginning point is to start with the conclusion and see if you can just find whatever your conclusion is sitting somewhere in your premises. If so, this will suggest clearly where a good starting point is. But if you can't do that, then strategy 15 comes into play. And again, strategy 15 says what you should do is try to deconstruct the conclusion so that you can now find the pieces you need to get to that conclusion somewhere in your premises. So to use the example that Hurley uses in the book, if I have the statement where premise 1 is if K, then it is either F or B, and premise 2 is G and K, but the conclusion is F and G or B and G, it is really difficult to see how you could get, at least at first glance, this entire conclusion anywhere in these two premises. But all the pieces are hanging out there. And so what we want to do is take the conclusion and start to tear it apart using our rules. And notice the first thing we can talk about here is that I have a situation where I can distribute G out, but I can't do that until I move G around with the two terms F and B. So the first step is to take F and G and swap them using the rules of commutativity. So instead of F and G, I get G and F. And then I can do the same thing to the other side. Instead of B and G, I get G and B. And notice at this point, we're in a position to use the rule of distribution. The rule of distribution now lets me pull G out and then put together F and B by way of an OR claim. So I get G and F or B, and then you can start to see how we're going to put these things together. Notice the G and part we can find in line 2, the F or B we find in line 1, and then it lends itself pretty quickly to figuring out how this would work. And once you do, you can just sort of reapply all of this reasoning backwards in order to construct a total proof. So that's an end to the first 5 of rules of replacement. The next video you'll have will deal with the next 5 rules of replacement.